Okay, guys, now we're going to talk about distributions of data. We've already talked about shape, skewing, a little bit about middle, the average. Most of you, I know that the average is that you add up each piece of the data, so you have all of them, and then you divide by n. Now, it turns out there's a different average, and that's called the population average. And we write this one mu, and this is the entire population average, or mean. This is called the sample average. So sometimes we actually have access to every single piece of data. For example, the ages of all the students at Augie, we have your birthdays, etc. Now, we happen to know that the average really is a balancing act. It's a fulcrum of where all the information is balanced, and it represents a middle. What other middles are there? Well, the mode is a middle. It is the most. But sometimes there's a tie, so you could have a data that looks like this, and then there's two modes, and we saw some histograms that we actually referred to as multimodal or bimodal. Why? Because the graph seems to have different high points in it. We understand that. But an interesting one, a very important one, is we call the median. The median is best thought as the man in the middle. So if you lined up all of the data in an order, so I don't know if x1's I, so I'll just call it xi, and it's less than or equal to xj, and it's less than or equal to xk, all the way less than or equal to some xn. They're in the order. The piece of data right in the middle is called the median. Now, what's nice about the median is literally half the data is above the median and half the data is below the median. The median is a very powerful thing. It's very descriptive. So let's demonstrate why that median is such a nice thing to know. Let's take a set of data, 10, 20, 30, 60. I'm going to put another data so I can divide easier. No, that's okay. I'll leave it there. So we have four pieces of data, and so 10 plus 20 plus 30 plus 60 divided by 4, 90, 120 divided by 4 is 30, and we discover there's the average. Now, if you put it on a teeter-totter, there's 10 located, there's a 20, and then there's a 30. Way over here, 40, 50 is the 60. And the reason it has to balance that way is these two are to the left of the mean, and that one's further away, so one can balance two of them. It was what we refer to as torque. However, the man in the middle here doesn't really exist. They're in order, and we have this general rule that is there's an even set of data. We call the median to be halfway between the two in the middle. Or in this case, we would say 25 is the median. And when that happens, half are above and half are below. Now let's add a piece to this data set. Let's do 10, 20, 30, 60, 800. Now that's pretty crazy. That's a big number compared to the others. And so this set of data, when you say 10 plus 20 plus 30 plus 60 plus 800 over 5, well, that's 920 over 5, which is 184. That's a big number. And so your average of your data is 184. Notice 4 lie to the left of it and just 1 to the right. This is what can happen with the mean. The mean can be heavily moved by a single large piece of data or a single small piece of data far to the left. This is why we don't like the mean sometimes. It doesn't really represent the middle. It represents a balanced middle. One big guy on a teeter-totter with a bunch of little people on the other side. But if you look at this data and you just simply order them and find the person in the middle, now 30 is exactly the person in the middle. So a lot of people feel that the idea that the median describes the middle as one of the best ways to describe a set of data, better than the mean. The mean can be affected by some strange numbers. Now, the mode is not necessarily a bad descriptor either, because if you have a very significant mode, it says a lot of people have that value. So that's rather interesting. So that's 3 different ways to talk about middleness, but we need to talk a little bit more about data, because data also has this concept called spread, the min and the max. So first off, let's just talk a little bit of what we call the 5-number summary. The 5-number summary says begin with the mean, begin with the max, and then find the median. Now we like to use capital M for the median, and that's broken your data into 2 sets. And so there's the stuff below and stuff above. And by the way, the median may not be in the data set because if it's an even number. Now we have this next rule that says if you cover up the median and all data below it, if you find the next median, the median of the upper half, we happen to call that Q3. And if you cover up the median and all numbers above it, we find the middle of the lower half, we call that Q1. And this creates 1, 2, 3, 4 pieces of data. The lower half of the bottom half, the upper half of the bottom half, the lower half of the upper half, and the upper half of the upper half. These are called quarters or quartiles. The median happens to also be called quartile 2. So we have the min, quartile 1, quartile 2, quartile 3, the max. And the rule is quite simply, find the median. Cover up everything up to including. You cover up the median, figure out the upper one, and then repeat it, figure out the lower one. Now, if we make this into the following picture, we call this a box and whisker picture. It's one way to show what the data looks like. Now, I've drawn very equally spaced box and whiskers, but that doesn't happen. So let me do a calculation here. Let's take a couple of ages of kids in a daycare. So here's a list of kids in a daycare. Now, there's not very many numbers here, so when you break up these quartiles and maxes, well, we'll see how this works. So the minimum of the data is 1. Maximum of the data is 6. Now, I'm going to find the man in the middle. One way to do that is just keep pairing up high and low. Halfway between 5 and 5 is 5. So there's the median. Now, this guy, 5 right here, halfway between these is the median. Now, if I cover up this guy and find the man in the middle here, I get a 6, because that guy's in the middle. If I cover up that 5 and I look at the man in the middle here, it's a 2. And there's what my box and whisker diagram looks like. And what it shows is that the lower half of the data is much more spread out than the upper half of the data. In fact, 50% are in a very small range. There's no whisker here, just a stub. It shows that the second quartile grouping here, from second quartile up to the median, is quite spread out. It's the biggest group for 25%. So we can see shape with this fairly limited concept of a 5-number summary. Now, it turns out there's another concept involved with the shape, But I don't want to get rid of the box and whiskers quite yet. I'm going to draw another box and whisker. And this box and whisker has 50% of the people are very, very nicely packed in a very regular space, because that's 25% there, 25, 25, 25. The upper 25% is very spread out. When you make a box and whisker diagram, you can see skewing, especially when one of the whiskers is really stretched out compared to the other ones. It's a useful way of describing a quick description of the distribution so that you can understand there's a variety of measurements in the upper 25%. Now, it turns out that we have one more very nice piece of information that we want to develop called the standard deviation. Now, those of you that have had any form of statistics before, you know that this is also a measurement, and it's derived from the sample or from the entire population. So we have a formula. It's kind of complicated. The idea is we want to add up how far and different people are away from average. So if you have a bunch of data, here's our data all spread out in order. Let's say our average is right here. This is much longer than this. We can measure how far something is above the average. And that measurement is quite simply, you take a data piece and you subtract off the average, and that measures what we call its deviation. Now, the problem with that measurement is that these are positive and these are negative, and they're going to add up and cancel each other. So if we square these, then we have all positive numbers, and we divide by how many we have. Now, it turns out I don't want to divide by n. It turns out we want to divide by n minus 1. So here comes a special symbol that says, add up all of the data minus the averages, square them, divide by n minus 1, where we have n pieces of data. This is called the variance, or s squared. If you want to find the standard deviation, well, you take the square root of this. Now, it's very useful to have a calculator to do this so that you don't have to crunch these things by hand. But if you take a look at your book, they do a crunch calculation about how they took the data. First thing they did is then figured out the average. The next thing is they figured out all the deviations. The next thing is they squared them. Next thing is they added them all up. And then they divided by n minus 1. And then they took the square root. This calculation is called the standard deviation. And it's a measurement derived from the sample. It's an alternate measure of spread, how far the stuff moves apart. Now, this alternate measurement of spread is extremely mathematically based. It is a very nice idea. And so I'm going to point out a consequence of this spread. So it turns out when we plot data and we make a histogram, let's make a silly, not totally symmetric, let's make some histogram of some sort of data here. And let's suppose the average sits right here. It turns out that this idea called the standard deviation does something very powerful. The standard deviation, x bar, and the standard deviation define a natural middle in a different way, as a group. What is that natural middle? Well, that natural middle is you take the standard deviation and subtract it from the average, take that number and go all the way up the standard deviation plus the average, and this becomes a grouping of individuals in your data set that generally is around somewhere to 50 to 70% of the people. It creates a middle group. And so you have this number, you calculate x bar minus s, you calculate x bar plus s, and you have created a group that usually is around 50 to 70% of the population. It can be more, it can be less, but it collects people together. Now the next thing that's really strange, if you make that standard, add 2 of these standard deviations, or subtract away 2 of these standard deviations, you've now moved further on your histogram, and now you have defined a huge chunk of people, and it's usually somewhere in the vicinity of 95% of all people are within 2 standard deviations in this calculation. Because of this property, the standard deviation is used very frequently to explain where you reside in any set of data. That where you reside is a super important idea, but it's most important when we see distributions that have a bell-shaped curve. So a bell-shaped curve is a commonly occurring curve, and then when we draw histograms, they look very similar to them, not necessarily exact. Let's suppose this is the distribution of ages of Augie students. There might be somebody here 16, 20, all the way up to, let's say, 24, and maybe a 27-year-old. So here's what our ages look like. What this picture is also talking about, it's talking about the standard middle of this graph probably is something like 18 to 22. We can see a spread, a fatness of the majority normal group. And then there's thinning out up here. Now, if we take 2 standard deviations, once we calculate this, we discover we probably have almost all of the people. And anything that lies outside of 2 standard deviations starts being defined as unusual, not that frequent of occurring. How many regular attending 27-year-olds at Augie are there? Don't know, but not a large group, and probably not very many 16-year-olds. So the standard deviation is a very powerful descriptor of most curves that look like this. Now, we can't exactly explain why this curve always seems to happen. But if I take heights, if I take weights, if I take IQs, I seem to get these over and over again. But if the population isn't homogeneous, like one group, then the weights of somebody group might look like this. It appears that there's more lighter people than heavier people, but there's 2 subpopulations. So normal curves, when put together, can tell us things about populations that aren't homogeneous, and we might search out in what is this population? What is going on here? We use this to analyze crime in different parts of cities, or parking tickets that are happening, and we wonder why, and they start investigating what's going on here. Now, some curves are more spread out than other curves, even though that they're normal. So one normal curve might be talking about ages, and look like this, 16 to 27. But another normal curve, talking about ages as well, let's say these are ages of students at Augie, that one might look like this, and it's really fat and much spread out, and it might be 19 to 45, yet it's still a bell-shaped curve. We say that this curve is narrower than that curve, that this curve is more distributed out. But it is very likely that the middle plus one standard deviation, middle plus one standard deviation has about the same amount of people. Two standard deviations away, two standard deviations, about the same amount of people. And we can use these groupings to say they're above average, below average, etc. Wider distribution, but still normal. Narrower distributions, but still normal. What describes that fatness? It is the standard deviation. The standard deviation of students in Augie is probably about 1 year. While the standard deviation of students at, let's say, a community college might be 3 years. They both could have a bell-shaped curve, but it takes a larger group of years, 6 years, 3 below, 3 above, before you get a large chunk of the population. Now, what's really weird about normal curves is we actually can describe precisely when something is very, very close to normal, how many people are in these groupings caused by moving your standard deviation. This is called the 68, 95, 99.7 rule. These two numbers we're going to use very frequently. This could appear in the homework. So when you have a normal distribution, a bell-shaped curve, it's symmetric. It's usually describing some measured parameter. And in the middle is an average. Now this might be an average of a sample, or it might be you've actually sampled absolutely everything and it's the population average. So be it. Now, we're going to calculate x bar plus s, which is the standard deviation of the sample. We have a symbol for the standard deviation of an entire population, and that is this funny Greek letter sigma. It looks like somebody with their hair blowing or whatever. And if we subtract off s, or we have the actual average minus the actual variance, standard deviation, sorry, we usually get approximately 68% of the population, which means we expect 34% here and 34% here. So, as an example, if a teacher says they use the normal curve and the average is the cutoff for a C, well, here's the C students and here's the D students. Or they might say, well, this is the normal middle. That's the average person. We'll make all of this the C. That's called grading on a curve. It's kind of taken a new meaning, but yeah, that's what it originally used to mean. 68% of the people got C's. Now, with a normal curve and a bell-shaped curve, if you move up 2 standard deviations, and if you happen to have calculated the entire data set, then you would write it this way. And you move down 2 standard deviations, whether it's 2 samples or the whole population, so we use different symbol. This is, again, the sample symbols versus the entire population. We use 2 different symbols to indicate we know a sample or not. Now, this rule says we now have 95% of the people. Well, we already had 68% here, so 95 minus 68 is 27, so we have 27% to go in these 2 places. Well, 13.5% go here, 13.5% go here, which says that 95% of the population lives within 2 standard deviations of the mean. And up here now, and down here are the more extremes. Now, we're not going to do the 3 standard deviations. Take a look in the book. What has to be left is 5%. So we have 5.5% here and 2.5% here. We refer to these as the way above average, the way below. Now, if we had been grading on a curve, this very possibly could have been F, D, and they put all of this C, B's, and A's. How'd you like to be in an educational system where we always guarantee only 2.5% people get A's, and 13.5% get B's, and 68% get C's? This curve makes a lot of people have C's. Most people pass. Very few people fail. There are countries that grade national exams on a curve, and this is how grades are administered. I don't think it'd be good for us. Now, what is the reason that we do this? The reason is this curve is the dominant curve that happens when you measure almost anything in a homogeneous population. You measure Scandinavians, blonde, blue-eyed, their heights will be normally distributed, their weights will be normally distributed. It's amazing how powerful this. You can go to Canada and measure German immigrants, and you get the same thing. Heights normally distributed, weights normally distributed. But as soon as the population is non-homogeneous, you start getting different things. So you take humans and you measure the length of your femur. Guess what? Amongst all humans, the length of our femur, when graphed, is going to look like a normal curve. It just has to happen over and over and over again. Measured quantities in a population that's homogeneous enough will have a normal curve. And that says we can measure where you fit. Now, let's suppose these were the times of kids in high school running a 100-meter race. What's an average time to run a 100-meter race? Let's say it's 12.5 seconds. No, that's rather fast. Let's make it 13 seconds. Well, do you want to be up at the 15-second group? In this direction, added time is not good. In this direction, reduced time is good. Again, direction is not always is not directly linked to good or bad. All right.